Drawing constitutional isomers, that'll be the topic of this lesson in my organic chemistry playlist. Now, we spent the entire first half of this chapter naming alkanes, and I will spend the latter half drawing different conformations of alkanes. And we'll start here with drawing constitutional isomers, but we'll move on to Newman projections and then different conformations for cycloalkanes, including the most famous, the cyclohexane chair conformation. Now, if this is your first time with me, welcome to Chad's Prep. My name is Chad, and the goal of the channel is simply to make science both understandable as well as even enjoyable. Now, this is my brand new organic chemistry playlist. I'll be releasing these lessons weekly throughout the 2020-21 school year. So if you don't want to miss one, subscribe to the channel, click the bell notifications. You'll be notified every time I post a new video. All right, so before we start actually drawing constitutional isomers, there's a little bit we got to talk about. And with hydrocarbons, we often talk about what's referred to as a saturated hydrocarbon versus an unsaturated. And this applies to like saturated fats versus unsaturated fats. And all that really means, saturated means you have the greatest number of hydrogens possible. So we know that carbon likes to make typically 4 bonds in most stable structures. And if you fill every available bonding position with a hydrogen, so on a hydrocarbon, then you're going to get a certain formula associated with that. And that formula looks something like this here, where you take the number of carbons, and if you double that number and add 2, that'll get you the saturated number. So in a little bit, we're going to be taking a look at a formula that has got 7 carbons. And the greatest number of hydrogens you could ever have with 7 carbons present, so in this case is double that number, 14, add an extra 2 to get to 16. And so the formula would be C7H16, and seeing this formula be like, oh yeah, the number of hydrogens is double the number of carbons plus 2, that's a saturated hydrocarbon. And we'll see where this kind of comes from here. So if we actually take our lovely 7 carbon structure and make it kind of in a straight chain here, we'll see that all the internal carbons to get to 4 bonds have room for 2 more hydrogens each. But the N2 carbons here, they have room not just for 2 hydrogens, but for 1 extra each, since they were missing an extra bond there. So same thing on the other end here. And that's where the extra 2 comes from. So every carbon in the chain has 2 hydrogens, but the ones on the end have 3 each, and that's where that plus 2 comes from. And so this would be a saturated formula. Now, where you get an unsaturated formula from, the most common place is if you stick and take and replace one of those single bonds with a double bond. When you put a pi bond in a structure, you'll note that these 2 carbons right now are violating the octet rule. This is not a real structure. So those 2 carbons each have 5 bonds now, not 4. So we have to kill a couple of hydrogens in order to incorporate that double bond in the structure. And so now we'd find out by putting a double bond in there, a pi bond, instead of having double as many, carbons plus 2, it's just double as many. So now, forgot to add that one there. So in this case with 7 carbons, instead of having 16 hydrogens, now we're only counting them up. You only got 14 hydrogens instead. And so every 2 hydrogens you're missing from that saturated formula is going to be a degree of unsaturation. And the easiest way to do it is a pi bond. Notice if I put a triple bond in there, I'd have to kill 2 more hydrogens. So for every pi bond, you're going to be missing a couple of hydrogens. Now the other thing you could do is you could join the ends together in a ring. And so when you join a ring, I'd have to kill a couple of hydrogens in that sense as well to make it so these 2 carbons could attach to each other. And so that's your other form of unsaturation. We call them degrees of unsaturation. So it's either a pi bond or it's a ring. And for every pi bond and every ring you have in your structure, you're going to be missing 2 hydrogens from your saturated formula. Now, somebody's come out, instead of looking at it that way, with what's called the Hydrogen Deficiency Index. And so in this case, if you take the number of carbons and double it, plus 2, and then subtract off the number of H's, subtract off the number of halogens, add the number of nitrogens, and then divide by 2, what that will give you essentially is how many elements of unsaturation or how many degrees of unsaturation you have. So like, let's say in this one right here, we've got the 7 carbons, 1, 2, 3, 4, 5, 6, 7. So 2 times 7 plus 2 minus the number of hydrogens. Well, in this case, we've got 14 hydrogens, no halogens, no nitrogens, and then divide by 2. And so in this case, 14 plus 2 is 16, minus 14 is 2, all divided by 2 would be 1. And this formula of C7H16 would have 1 degree of unsaturation. That would mean either 1 pi bond or 1 ring. So this is one quick way to get you that number of degrees of unsaturation. That's what that hydrogen deficiency index is. Cool. Now this is useful when you're being asked to draw constitutional isomers, because if you're given a formula like this one here, we're going to draw the constitutional isomers of C7H16 in a minute, which you might want to know as well, do I have to incorporate any pi bonds or rings in my structures? And in this case, with 16 being double 7 plus 2, I would see, nope, there are no degrees of unsaturation. It is a saturated hydrocarbon, and so none of my structures are going to get a pi bond or a ring. Now, on the other hand, if I was having you draw all the constitutional isomers of C7H14, now all of a sudden, every single structure you'd have to draw would have 1 degree of unsaturation. Every structure would either have 1 pi bond, and you'd have lots of different places you could put it, or you'd have to have a ring, one or the other. So, and that's kind of what you can get out of this formula. Now, most of the time in this section, again, this is a whole chapter on alkanes, you're going to pretty much be, in all likelihood, asked to draw the constitutional isomers of a saturated hydrocarbon, but on the odd chance that you're not, that's why we kind of covered this. But I just want to make sure we're verifying that we've got saturated hydrocarbons before we start trying to draw these structures. All right, so now we're going to start drawing these constitutional isomers for C7H16 proper. Now, if you got the study guide in front of you, they're already there, but probably good practice if you did make an effort to write these on your own. And rather than writing these in any kind of bond line structure, I find that it's easiest if we kind of represent them in more of a Lewis structure. Now, one thing to note here, so my question for you, and I'm going to give you the answer obviously in a second, is what is the bond angle between these two bonds right here around this carbon? And again, just picture that this carbon is going to end up with a couple more bonds on it as well. But my question for you is, if you look at the two adjacent bonds, what's that bond angle right there? But also if you look at the two opposite bonds coming off that carbon, what's that bond angle? So, and if you said 90 and 180, so be super careful. This carbon is sp3 hybridized, and all of its bond angles are 109.5, regardless of how Mr. Lewis makes it look. Now, Mr. Lewis makes everything look either 90 or 180, but regardless of how you look at it, this angle right here is 109.5, and this angle is 109.5 as well. And the reason I bring that up is a lot of students will say, yep, Chad, we're going to draw some carbon backbones here, and they come up with this one right here, and we're just going to fill in the hydrogens later. So, but if you get the carbon backbone, and based on knowing that this is saturated, we know we don't need any double bonds, so it'll be a lot easier to come out than if you try to do this with like a bond line structure from the start anyways. So, but in this case, a lot of students will come and go for a second one here. So 1, 2, 3, 4, 5, 6, and 7. And they'll do something like this. And they'll be like, so this is different, Chad. I'm like, nope, that's the same thing as the one we just did. Because my question would be, what's the angle between these two bonds? Well, it's 109.5. What's the angle between these two bonds? Well, it's 109.5, no matter how we draw it like this. I still have 7 carbons in a straight chain. And if I fill in all the hydrogens, it'll be exactly the same thing as this structure with all of its hydrogens filled in as well. So just want to make sure we realize that I can, zig and zag and stuff. But as long as my longest continuous chain kind of is 7 carbons here, in a straight chain, regardless of how I zig and zag, it's the same molecule. All right, so we're going to take a systematic approach here to drawing these constitutional isomers. And what you want to do, it's not the only systematic approach, it's just the one I recommend, is you start with your longest straight chain and then slowly but surely shorten it up. So in this case, this is going to be 7 carbons in a straight chain, not too bad. And eventually we would just go back in and fill in all the hydrogens. So if you're asked to do this on an exam, obviously start here, draw in all the carbons, and then just save room because you're going to go back in and draw in all the hydrogens later. And if you had to turn that into a bond line structure, you just go 1, 2, 3, 4, 5, 6, 7 when you're done. Cool. Now to get the other constitutional isomers, what we want to do now is go back and say, well, let's shorten that longest chain from 7 carbons, which is the entire chain here, down to 6. And so we'd go 1, 2, 3, 4, 5, 6. And then we ask ourselves the question and say, okay, where do I put that last carbon? Because now that I'm down to 6 carbons, I've got 1 carbon left. And the key is you can't attach him to either end, because if I attach him to either end, whether I put him here, here, or here, it's going to lead me to a situation where I've got like this again, where I've got my longest chain is going to be 7 carbons long continuously, just like we did up here, and it'll be no different than when we draw. So when we start shortening the chain up, we're going to make sure we can't add any of the carbons we've got to fill in to the ends, or it will go back to being a longer carbon chain than just the 6 we got here. But in this case, I've got all these middle carbons, and I can add that extra carbon onto any one of them. Now, so let's say I decide to put it here. Well, one thing you should realize is that's no different at this point than to putting it here. Because this angle is 109.5, that angle is going to be 109.5. It's the same thing either way. You should also realize that it's no different than adding it either here or here as well. So whether it's the second carbon in from the left where I put that extra carbon, that 7th carbon, or the second one in from the right where I put that 7th carbon, it's the same thing either way, just the whole molecule rotated around 180. But it's the same thing. So there's no difference there. So whether I put it here or here, that 7th carbon, that's going to be one of my structures. Now, moving right on down the chain then. So 1, 2, 3, 4, 5, 6. And so I've considered adding it to one of these carbons, but then I could add it to one of these as well. And whether it's the 3rd from the left or 3rd from the right, that'll be the same thing. And so as long as I put that carbon in any one of these 4 positions, that'll be another constitutional isomer. And again, we would just then go back and fill in all the hydrogens and stuff. Cool, but that's it. As far as 6 carbons, I've exhausted all the places I could put that extra carbon and still have my longest chain be 6 carbons long. Now, if I needed to go back and, draw the bond line structures, so 1, 2, 3, 4, 5, 6. So there's 6 carbons long, and the second one from the end gets another carbon, or this one here. And now it's the 3rd one in from either end that gets a carbon. And whether I put it here or here would have been the same thing either way. So if at the end you've got to translate these back into bond line structures, like based on the instructions on your exam or something like that, great. But I would highly recommend setting it up like Lewis structures and just set up the carbon backbones, because these will be easy enough to draw after the fact. All right, so we did 7 carbons in a straight chain. Then we made our longest chain 6 carbons and added that extra carbon. Now we'll drop this down to 5 carbons as well. All right, so now if we make our longest chain 1, 2, 3, 4, 5, now we've got 2 carbons remaining that we have to add onto this structure. And again, I can't add it onto the ends or end up with something longer than a 5 carbon chain. And we've already considered all the possibilities of something longer than a 5 carbon chain continuously. So I've really got to put it on the middle carbons here. I've got these 6 positions to work with to put those remaining 2 carbons. Now I've got a choice. I can do 2 methyl groups, 2 separate methyl groups in 2 different of these 6 locations. That's an option. Or I could do a single ethyl group. Now we got to be careful though, because you can't just put that ethyl group anywhere. And the truth is I can't put the ethyl group either here or here at all, because if I do, like let's just say we made it an ethyl group, 2 carbon chain, a 2 carbon branch. Now my longest continuous chain would not be these 5 carbons, it would be these 1, 2, 3, 4, 5, 6 carbons. And this would actually be the same thing as this guy right here. So drawn a little differently, but it's exactly the same thing. So we couldn't just put an ethyl group on either. Again, we can't put anything on the ends, but we couldn't put a 2 carbon chain, 1 carbon in as well, or we'd get a longer continuous carbon chain than the one we are intending to get. So, but I could put that ethyl group on this guy right here, and that would indeed be something new. This could still be my longest chain, or this, or this. So, but my longest carbon chain is still 5 carbons, but that's the only place, whether I put it down below or up above, same diff, but that's the only place I can put that 2 carbon chain. So now I've got to draw again 5 carbons. And once again, these are my 6 positions where I have an option to put something other than a hydrogen. And I could do 2 methyl groups as well. Now, one way to do this would be to put both methyl groups attached to the same carbon. So whether I put it both on this carbon or both on this carbon here, that would be exactly the same thing. So, but I could also put them both on the middle carbon, and that would be a unique structure as well. All right, so however, we could consider also putting them on 2 different carbons. Let's make ourselves just a little bit of room here. All right, so once again, I've got these 6 positions to work with. So, and with 2 methyl groups on 2 different carbons, well, I could put one here and one here. So, and again, it doesn't really matter if I put one up here or down here and then up here or down here, whether I put that there or there, it's all the same thing. So as long as it's one each on these 2 carbons, that's one way to do this. Now we've got one more way to pull this off as well. So instead of doing these 2 carbons, I could either choose these 2 or these 2, but essentially that'd just be the same thing flipped 180. And again, whether I put them both on top or both on bottom or one on top and one on bottom, it's all the same thing. Cool, and this would be the last kind of carbon backbone I could set up. And once again, once we get the carbon backbones, we can just go back in and fill in all the hydrogens. And if a Lewis structure is acceptable according to your exam instructions, great. But if you got to go back and translate these into bond line structures, that's easy enough to do once you got your carbon skeleton as well. All right, so now we've gone from 7 carbon straight chain down to 2 possibilities we had with a 6 carbon longest chain. And now we've got 5 different possibilities when we've got a 5 carbon longest chain. So now let's shorten this down to 4 carbons. So we're starting to run out of room on my little board here. So, but we're going to start running into some major problems here. So because with 4 carbons here, I've got 3 carbons remaining. And again, you can't put anything on the ends or you end up with something longer than a 4 carbon chain. So you only got these 4 positions in which to put things. And I've still got 3 carbons remaining. Now, again, with 3 carbons remaining, I could just use one propyl group, one 3 carbon branch. But that's not going to work, because if I just put a 3 carbon branch here, so all of a sudden this becomes my longest chain, and that's one of the possibilities we already considered. So if I want to put a 3 carbon branch on something and not have it be something I've already covered, it's got to be at least 3 carbons in from the end, and that's not possible here. So, and if I want to put even an ethyl group on something, it would have to be on a carbon that's at least 2 carbons from the end, and that's not possible here, because these each are only 1 carbon from an end. So the only thing we can put on these in any of these 4 positions are a single carbon methyl groups, and I've just got to choose 3 out of the 4. And so in this case, with 3 out of these 4 getting chosen to have a carbon, there's 2, and whether I put one here or here, it's just the same thing flipped over. So in filling 3 out of those 4 positions, it turns out no matter how you do it, it actually all ends up being equivalent. There's only one ultimate way to pull this off, and so there you've got your 1 4 carbon longest chain as well. So here we had a 7 carbon chain, 2 versions where the 6 carbon chain was the longest, 5 versions where we had a 5 carbon chain as the longest continuous chain, and then finally 1 option where a 4 carbon chain was the longest. But these would now represent all of the constitutional isomers for C7H16. Okay, so the last one was all on your study guide. So, but this one is totally on you. I want to make sure you have to draw this one out instead of just being like, yep, I put all these, Chad already put them on the board, but they're already on the handout, so life is good. But in this case, you're going to draw these out. So, and I put an oxygen in there just in case. It's not necessarily something you will come across here, but many classes would be on the hook for something like this. Now, it turns out that oxygen is not part of your calculation for determining degrees of unsaturation or the hydrogen deficiency index. We can just kind of ignore it and pretend it's not there. And for 4 carbons, the greatest number of hydrogens you could get, well, double 4 is 8, plus 2 is 10, and we have a saturated molecule again. And again, what that means is no pi bonds and no rings in our structure whatsoever. Now, one thing you should keep in mind for oxygen is oxygen tends to make 2 bonds, being 2 electrons shy of a filled octet. And so with oxygen making 2 bonds, that means it also could go in the middle of the carbon chain, and something we might have to consider for a possibility. So, but we'll start in drawing constitutional isomers for this with the longest carbon chain we could have, a straight 4 carbon chain. So 1, 2, 3, 4. And now we've got to figure out where to put the oxygen. How many different places there are there for putting the oxygen? Well, in this case, I could put the oxygen on either end, like so, or I could put it on either of the middle carbons, 1 carbon in from either end, and that would be a unique location. And then from here we get, go back in and fill in all the H's. And just keep in mind that oxygen needing 2 bonds would also need 1 more H on this structure as well. Cool, but as long as we don't put any pi bonds or rings in there, we'd end up with room for exactly 10 hydrogens, being again that this is a saturated molecule. Cool, now for a 4 carbon straight chain, those are my options for where I could place the oxygen as long as it's not incorporated into the middle of the chain. Now let's shorten this down to 3 carbons. So, and with 3 carbons, my 4th carbon is going to have to go as a branch on that middle carbon, whether it be up or down is totally doesn't matter. And the question is now, where can I attach that oxygen? Well, on a structure like this, whether I attach the oxygen to this carbon, or this carbon, they're all equivalent. Just rotate this thing around a little bit. And so I'm just going to make one of the structures with the oxygen here. But the other place the oxygen could have gone was that carbon, which is definitely different than these 3. And so that's another option. And we'll find out here, we can't actually shorten the chain down any shorter. We went from 4 carbons down to 3 carbons, but you can't really go down to 2 carbons because then both are the ends and you can't add anything to the ends or you get a longer chain. However, we can consider possibilities where the oxygen is in the middle of the chain. So every single one of these is going to have an OH. You'll add an H to the oxygen in every case. These are all alcohols. But if you put the oxygen in the middle of the chain and bond it to 2 carbons, we'll have ethers instead. And so in this case, we could do this one of a couple of different ways. We could have 3 carbons on one side of the oxygen and 1 carbon on the other side. We could have 2 carbons on one side of the oxygen and then 2 carbons on the other side. And notice if I made it then 1 on this side and 3 on this side, it'd be no different than what we did up here. And then you've got to consider, well, can either of these carbon chains have any kind of branched equivalent as well? So, well, with 2 and 2, there's no way for that to be any different than what it is. And for a 1 carbon chain here, there's nothing you can do with that as well. But for 3 carbons, you can bond that through one of the end carbons, but you could also potentially bond it to the oxygen through the middle carbon as well. And so what you could also then do is something like that as another possible structure as well. And so in this case, with putting the oxygen in the middle of the chain, we've now created 3 new possibilities as well. And again, we just had to look at putting in the middle of the chain, breaking it up and saying how many carbons can go on both sides. And we can either do it 3 and 1 or 2 and 2. And then with 3 and 1, there were 2 different ways of pulling this off. And so in this case, we found out for C4H10O, there are indeed 7 different constitutional isomers, 4 that were alcohols, 3 that were ethers. And again, from here, you just fill in the hydrogens or draw the corresponding bond line structures. Now, if you found this lesson helpful, consider giving me a like and a share, pretty much the best things you can do to support the channel. And if you're looking for practice problems or if you're looking for the study guide that goes with these lessons, check out my premium course on chadsprep.com.